Okay, so we started with what we call the, after the data pre-processing, we started with what we call the machine learning model development. So there are stages. If you look at the flow diagram that we shared with you, there are stages of model, stages that we follow to develop machine learning model. Okay. One of it is, first, you need to have your data, which we have discussed already about that. The second thing is you need to pre-process the data, which we have also talked about that. The other components that we have left out in the data pre-processing state is what we call the feature engineering. Even though it was touched on briefly, it's an important component in that. So touch on briefly. So the pre-processing, then the feature engineering, and then we also have what we call class imbalance or class balance imbalance. Then we have what we call feature importance. So those aspects that are we haven't touched on will be touched on with you so that you have a full picture of that. And then the techniques that are used in doing those things, we'll touch on those things with you on that. Then after the feature process, after the data processing, which includes feature process, pre-processing and feature engineering and the others, then we now came to now the data is ready. So we now have, of course, let me also add that the last one is then the data encoding. All those things are there. Then we now came to the data itself. So we now have the real data that is ready for the model development. Now, to develop the model, there are things that we talked about. One is that first, you will not want to use all the data to train the machine learning model or to train a model or to develop a model. You will not want to use all your data to do that. Who can tell me why we think it is important not to use all the data to develop the model? Anybody? Why is it important that we don't use all the data to train the model? Yes, Sheriff.
Yes, Doc. Please, I think so that later on when we are done with the developments, we can test and see whether actually it's giving us the output we want.
Very good. So you will not want to use all because of the reason that he has given. Now, when your model has become very familiar with all the data that you have, then it will be very difficult to know whether the model is working well or not. So what you do is you keep part of the data and then you use the rest to it. And another thing also is that we don't divide the data into 50-50 to do that. Because if we do that, then we may not have enough data to train the model. What do we mean by enough data? When we talk about training, there are different scenarios that information. Today, for example, you ate breakfast at 6 o'clock. Tomorrow, you eat breakfast at maybe 6:30. The next day, you may eat breakfast at 8 o'clock. The next time, you eat 7:30. So you see that if your breakfast has been between 6 and 7, then when you have the model that has something, you now have something that has to do with it. It will see it as strange. So you need to have various variations of the information so that at different part of it, so the model will be able to learn the different aspects of you. In the same way, some of you, for example, your mobile phones that you have, when you are setting it up, they will ask you to use either your fingerprint or maybe the face, and they will ask you to do many times. That's the reason. Because one time is not enough. So many times your face will not be exactly the same 100% location. Maybe to shift a little small, maybe you turn some way small. So you looks at various aspects of it to show that you are the same one and only person. That's what it is. So when we have the data, we try to split the data. There is no clear empirical formula that says that when your data size is 10,000, you should use this or use that. But the general rule of thumb is that it is important to use as most data for the training as possible. So some use typically 70%. Others use 70% of the data for training and then 30% for testing and validation. Some also use 75% for training and then 25% for testing and validation. Some also use 80% for training and then 20% for testing and validation. So it depends on your individual approach. But at least the conservative is maybe between 17 and 80% of the data for training. And then you should also have some enough data for testing and also to validate your model. So the data will be split into two parts, one part for training and another part for testing and validation. I'm using the word testing and validation. We need to validate. After testing, we validate. Okay. So that is the data will split. Now, after the data has been splitted, as we took you through, see that you use, I think 70-30. That was the model, the last Tuesday one, 70-30. Now, then the next one was, after you have done that, now you have to now identify which of the machine learning algorithms you want to use to develop a model. Again, my language, machine learning algorithms. Which of the algorithms you want to use to develop a model? And then Ken showed you last Tuesday about the process. We have two broad categories, either supervised or unsupervised. Of course, there are others like reinforcement, semi-supervised, but broadly, we have supervised or unsupervised. So if the data that you have contains some labels means that you have the input and the corresponding output, then the best machine learning algorithm to use is what we call a supervised learning algorithm. Now, under the supervised learning algorithms, there are a lot of algorithms, which we are going to take. If you look at the outline we gave to you, we are going to deal with most popular supervised learning algorithms that are used. Right. Then, okay, you want to show something?
Yes, I was trying to project the parts where the algorithms, yeah.
I think it is before. It should be either 10, like slide 10 or 11 or something like that.
Okay. Yeah, I think most of them are here, yeah.
Okay. Right. So you identify based on your data, you identify the type of machine learning algorithm you want to consider for your model development. Now, this is where when you are using it for your final year project or graduate level, then I will not take one for an answer because that's not the engineering way of doing things. So if somebody decides that, oh, I want to use random forest, or I want to use naive Bayes. These are things that will be taking you through each of them. Do you see how we are going to spend a lot of time on these things? So assuming that you tell me that, oh, you use, maybe Mariama says, oh, she is developing a solution. Maybe I'm working with her on the, Mariama, which department are you?
Biomed.
Very good. I work with biomed students a lot. So if I'm working with you and then you tell me that, oh, you develop this and then you use naive Bayes or random forest for your solution, the first question I will ask you is, why did you use that? Not in a very big voice, but I say, well, why should you use random forest? What motivated you to use random forest? So engineering solutions, we try different options. And then we select the best one that will give us a solution. So in machine learning model development, you will decide that, okay, I want to use maybe 4, 5, 6 supervised learning algorithms. No problem. So you now select maybe support vector machine, decision tree, maybe naive Bayes, logistic regression, maybe shallow network or deep network. Now, then you go through and then you test every one of them. When you test every one of them with the same data that you have, and the same data for the training, the same data for the testing. And then each of them, when you have tested each of them, you now record each of them, their performance in detecting whatever you want to do. Each of them. And then so in a tabular form, each of them, their performance. Another thing too that we are also interested in is, I don't know, maybe Ken will talk about it today, is what we call the computational time for a model development or the learning and also the testing. How long does it take for your algorithm to learn a particular problem? And how long does it take to test? But typically, we are interested in the learning time. And the simple reason why we are interested in this, if you are dealing with real-time solutions and it's going to take 2 hours, then it's not worth, there's something like, then it's not real time. Then we are not interested in that. So we would expect that you give us all the various algorithms that you have trained your model on, you have trained your data on, and then each of them you give us these outputs.
As well.
Nanaya, please. So once you let us know these things, then it is clear for everybody to see that, oh, maybe the naive Bayes was giving this result. This was, so each of them, you now have your list of results. Then out of the results that you have, then you can now say, okay, this one is giving the best performance, so I will take this. The reason why, again, we are interested in what we call the training performance and the testing performance is that we want to be sure that the model has not overfitted or underfitted. So if your training performance is reasonably close to the testing performance, then we say that, yes, the model has achieved a good performance. So there's no overfitting in that. But if your model is giving you performance of 80, 93%, and the testing performance is 63%, then there's a problem somewhere. So you now have to now go and dig to find out why it is so. If there is that performance problem, then the first question somebody will ask is, did you check the data, whether it is balanced or unbalanced? You see where the direct, so now, then we now go back to the data, whether we look at balancing, or if the class category is not balanced well, then we go back and then we do the balancing. So we go back again to the data. So at the end of it, we have to now find a way to get all those things. So when Mariama has done all these things, then she presents the results that, okay, these are the, so out of the, I look at all these performances. I look at the training performance, the testing performance, and also the build time. Maybe naive Bayes has performance close to the maybe random forest performance. Let's say they were all about, one is 92.5, another one is 93.5. And then the random forest being 93.5 has a model build time or model development time of 60 minutes or 600 seconds. Whereas the naive Bayes has performance of 92.7, but the model build time of 50 seconds. Now, then we have something we call trade-off. trade-off. So now the trade-off, which one do you take? Are you interested in real time or you are interested in performance? So there must be some decision that has to be made. So then you, the engineer, has to now make that decision. And then out of that, you will make a decision. Okay, based on these decisions, Mariama will tell me, based on these decisions, I selected, let's say, random forest for the model development. So now it is clear that you are now going to use now random forest. So now after you have now taken the random forest, then you now go through the details of it now. You now go through what we call the hyperparameter tune, all those sort of things will now come in because now you have settled on the particular model algorithm you are using. You have settled on the particular algorithm you are going to use for your development. And then she'll now go much deeper into that to do all the parameter fine-tuning on and on and on to now come up with a full development process. So what we have taken you through is now the choice. So how do you select? But let's assume you selected your machine learning algorithm. Then from there, you start the development. So the very first one that we introduced you to is what we call the neural network. So the neural network, that was one of the fundamental discussions we had with you, or introduction we gave to you as to how the brain structure is used, the human brain structure is used to train data to solve a particular problem. And we mentioned to you that there are two types of what we call neural network that we use for the learning process. One is what we call a shallow neural network, and the other one is what we call a deep neural network. So what Ken has started with you is what we call a shallow neural network, where you have the input. It has a 3-layer structure: the input layer, the hidden layer, and then the output layer. The input layer, they are only placeholders. Input layer are only placeholders. So they only hold on. They are nodes that we use to represent our input data or variable. The input data or variable. So that is the input. So they don't perform any computation. That is the input layer, neurons. Then we come to the first computational layer, which is the hidden layer, the first hidden layer. So this is what he also explained. I think, again, we explained to you from the beginning, the neural network. So now each neuron performs a numerical computation. Very simple. It performs summation and it performs transformation. Summation, transformation. Summation, every neuron performs that. Performs summation and also performs what we call transformation. The transformation is what we call now moving the summation data to the output. And we talk about different modes, mechanisms that are used. So that transformation method is known as activation operation. So we explain to you what these various activation operations that are used. One is a logistic regression. One is a hyperbolic time function. The other one is softmax. The other one is linear, on and on and on. These are all functions. The other one is rectified linear unit, various types that are used. Now, we explained those things to you for you at that time. But now you are seeing the role these ones are playing now. And they only deal with when you are dealing with neural networks. Okay, so the each neuron will now perform an operation, and then you give you an output. So for the shallow neural network, we have the input layer, which doesn't perform any numerical computation, only holds the input data. And the first layer, computational layer, is the first hidden layer or the hidden layer. And then the output layer is where your output is supposed to come out from. So depending on what we are dealing now, we're dealing with iris flower that has 4 outputs. Is it 4 or 3? I think 3 or 4, one of them. Right. So 3 or 4 outputs. Now, the outputs that we are talking about for a machine learning designer, thank you, Mariama. So for Mariama designing this, she has to decide how many outputs she wants. Assuming she was going to use this for maybe detecting maybe cancer issues, or let's say cancer, or maybe different categories of cancer. Let's say we have about 4 different types of cancer in patients, and she wants to test. Mariama, can I ask you a question again? You have 4 categories of cancers you want to test. How many layers, how many neurons will you put at the output?
Please 4.
Why 4?
Because since I want to detect 4 cancer, it means that the outputs, that the expected outputs are also 4. So 4 neurons at the output layer will be okay.
Okay. Who agrees with her? Who doesn't agree with her? Who agrees? Who doesn't agree with her? So it appears we all agree with her.
I agree.
It appears, but I don't agree with her. So, do you know the reason why I don't agree with her?
No, please.
Marama, so if I come to the hospital now, and then you test and I don't have cancer, how will you represent it?
Okay.
You now see there is, so when you are
Yes.
designing something like this for a hospital, then you also make provision for a case where a patient will come and doesn't have cancer. So that is how we deal with situations like that. So for such a solution, then you have a case where there's no cancer or unknown, because you have only talked about 4 cancers. So you may have symptoms. Then if it means that all the patients that will come, if you expect them to have symptoms relating to each of the cancers. How about if a patient has a symptom that is not part of any of the list that you have over there? So you see that then, so you see you have now, your solutions are going to change. You are not going to have more than the 4 that you intended. So somebody will come without any symptoms at all. So that person can belong to no cancer. And that person can come with symptoms that are not part of the other 4 categories that you have. So that can be unknown. So this is how we develop solutions. Anyway, I don't want to go too much into that. But so you now select the model. And so what if it is, what we have done, that's a shallow neural network. That's what we have just done. So now from there, if you think that your solution can start with, I think 5 hidden layer, 5 hidden neurons. The 5 hidden neurons, then we ask ourselves, is 5 okay? There is also no empirical formula anywhere that will tell you when you have a data or input neurons of this, use this number. There's nothing like that. People have tried to come up with some ideas, but it doesn't really apply to everything. So this is, again, some of the things that we do. So you test the input layers. You start with a certain number, let's say 4, 5. Then you start increasing the input, the hidden layers. You start increasing them. And with the same data, with the same information. And you see, to get to a point where the output is saturated. In that case, the number of hidden layer, you may not have. So you have, as and when you do, then you record your results until you get to a saturation point. So when you come back and you tell somebody that, okay, I settle on this number of hidden layer neurons, then there is basis for your decision. There is basis for your decision. Just let me show you something briefly. Just then I hand over to Ken to continue. This is one of the papers that we submitted recently that yesterday they have accepted. They asked me to do a final proof so that they publish it. So I just want to show you some small aspect of, so that you have an idea of what I am talking about. This is final manuscript, then okay. Let me see. Okay. Okay, so I'll just show you this. Oh. Okay. So okay, please, are you seeing the slide?
Yes, please.
Yeah, so you see, this is one of them. You see that what we have done here, we have one hidden layer with 5 neurons, one hidden layer with 10 neurons, one hidden layer with 20 neurons, one hidden layer with 25 neurons, one hidden layer with 30 neurons. So you can see the various performance levels that are going up. Then it got to a point, it started going down. And each of them, you have the time. So you can see some of the model development time vis-a-vis the performance. So this is how, then we now move on to 2 hidden layers, move on to 3 hidden layers, on and on and on. So this is how, when we are working with each of them, this is how they work out. So you see that in model development, you don't just say that, oh, this is what you are using, but at each of the times, you have to test, go beyond the normal way of saying that, oh, this one is working. How do you know? How do you know that one is working? So these are the ways we work on things like that. So at least this is at the beginning. So when you develop your skill set, you see that you go up and up and up and up, and you'll be able to do greater things with ML solutions. So I will hand over to Ken now, at least from where we have reached now to take us through from where we ended to conclude the process. And then if there are any things that he has for us for today. At the end of today, then what all of you have agreed, at the end of today, then we close. I hope that was the agreement, isn't it?
So I think the agreement is we pause or we take a break. I think
that's what I'm saying. Yeah. So
okay.
we close for that. We close for some which. Okay, so that's the appropriate choice of words.
Okay.
So we pause for some time, maybe 1 week, 2 weeks, depending on when they will be ready. Okay, Ken, so you can please go ahead.
Okay, thank you very much, and good morning once again to everyone. So today we are going to conclude on some of the things we started on Tuesday. And yes, I think the video is up, so please watch the video because we cannot go back to what we covered. But then, like we saw last Tuesday, we had a very good foundation of whatever thing we were doing, and we were trying to draw some inspiration from some materials that were already shared with us. So what I have over here is definitely what we dealt with, and we're guided by this flowchart. And like Dr. Mills rightly said, we had a lot of things dealing with the data. So we load the data, we do a pre-processing, and in drawing comparison, this was that stage where we loaded the data. Okay, so we used pandas and we relied on the read CSV method in there, and we had our iris.csv. So that was done. And then we went to the second stage where we did the pre-processing. So with the pre-processing, because we are a little bit familiar with these data sets, we knew that there wasn't too much problems with the original data set. But then with some data that you may have probably from a lab or something, you would have to look through deep into it and do an in-depth pre-processing. So we did dataset.info, and we saw that indeed there were no null values over it because everything was matching up with the total number of entries. Now we had to partition our data sets, okay? And the reason we needed to do that was because we are doing supervised learning now. And with supervised learning, we have to bring the input data and its corresponding output and feed it into the model for the model to learn. So what we did over here was to define, sorry, our input and output variables. So we said the input variable is going to be equal to the original data set, and we are dropping the IDs and the species. We dropped the IDs because the ID wasn't adding up anything to us. These were just sequential values, 1 to, I think, 150. That didn't add any value. And then the species, we had to drop them because those were our labels. So that's going to be the Y or the output side. So this was our X input. So we did a preview and we saw that, okay, now we just have the 4 variables, which were the sepal length CM, the sepal width CM, the petal length CM, and the petal width CM. Then we did same on the other side where we're looking at the output. So with the outputs, once again, we grabbed our data set, which is the original data set, and we only sliced out the species. And this is where we have all the classes. Okay, so Iris setosa, Iris versicolor, and Iris virginica with all those species. So now we do a little bit of pre-processing, at least with this particular data set, in the sense that we want to change the target output to some categorical labels. And we saw we using label encoder, I think last week, and we applied that concept over here. So what we wanted to do, because we are going to build a neural network model for this, and the fact that based on the calculations that we saw over here, that when we apply or when we multiply the inputs by the randomly generated weights and we get a value, that value is going to be compared to our target. Now, initially, the original data set I had for this had males and females as the label names or the classes. And we cannot do male minus this to get the error, okay? So we needed to change these into categorical input so that we can at least do some subtractions over there. That's the same concept you're applying over here because you don't want to have Iris setosa minus something or Iris versicolor minus something, but then we can do, for instance, a 1 minus some value that we are going to get the error and propagate it back into our system to update the weights. So we ended up with this where we saw that everything was now changed from those strange values into some numerical values. So now everything was set. We've done our pre-processing. So now we have gone through this phase to do that pre-processing. We now have our data and we needed to do the splitting. So we came down here that, okay, in order to go about this splitting very well, we could have just split it on any axis or in any level. And that wouldn't have helped us so much because the computer naturally can learn from patterns. But then we want to randomize things such that, yes, even though there's a pattern to maybe the sequence in which the numbers are following, if we use the train test splits, it shuffles everything together. Now, that train test split is going to split our data set or whatever data set we provided into 4 subcomponents, okay? And these 4 subcomponents is what I showed up over here. Already, let's assume this is Iris setosa, Iris versicolor, Iris, the sepal length CM, sepal width CM, and whatever. And these are the labels. And what we have over here is like that we, So this is the split, okay, and we are seeing that this is going to be the X train, and this is going to be the Y train, because this is a Y output, and this is going to be the X test and the Y test. So we have 4 chunks of our data. Now, in that 4 chunks, we are going to train, because we build that sequential model over here. And in order to build that model, we went through Keras. So we said from Keras.models, we want to have a sequential model. That is going to kind of give us that skeleton that we can have the layers in that sequential order. And then we also saw that we can have a dense layer where we are going to stack neurons on top of each other, like the structure we see over here. So in this particular cell, we instantiate the model. So we say model is equal to sequential. And once again, like I said, this is giving us that skeleton. And then what we do over here is we now start adding the layers. So like Dr. Mills rightly said, this is going to constitute the first layer, or the input layer, which is more or less like placeholders for our input variables to now be fed into our network. And over here, we specify the input shape. So I showed you why the input shape is very important, because at the end of the day, there'll be some multiplications, and we needed to make sure that things are structured in a way that makes sense. Now, in this particular instance, we are seeing that the input shape is equal to 4, nothing over here. And we saw the reason why, because each input is going to be fed in row by row, okay? So in the first row, it's just going to have, it's just like a 1D array, and that's why we do that over there. And then we specify the activation function relu. Like I did say, we'll come back to the nitty-gritties of which activation functions we should choose. But I think the initial things that we did should probably set you on a good path now. At least go back and go and revise on some of them, and you understand some of these things. Then in the second layer, practically the first layer as we have over here, we are putting 5 neurons over here. So we specify these numbers we have are represented the neurons. So we have 5 over here, and the activation function we put out over here is rel. We don't put an input shape over here because this is a sequential model that we have built. So it is going to form that architecture for us. And then finally, for the dense, the final layer, we put in a 3 neuron over here, because we are just doing classification where we have 3 classes. And then we have an activation function, and we are putting softmax over here. So we did a model.summary to get a summary of our model. So we saw that, okay, the various layers that we specified were showing up, and their output shape and the number of parameters that are going to be trained. And now we want to see the weights. So there's a method over there called getWeight, or get_weight. So we did model.get_weight, and we saved it in a variable called initial weights. We did a preview, and we saw that these were the randomly generated weights that is given to us even before we start our training. Now, we haven't started our training yet. We just built that framework or that architecture of our neural network. So we come in here to start the training. But before we do the training, we needed to put up some parameters. So the first parameter we put up over here was the optimizer. And this optimizer has in there the learning rate and other things that is going to help with the update of the weights. And now we pass in a loss function over here. And over here, we are using the sparse categorical cross entropy. And we want to keep track of the accuracy. And that's why we have the accuracy printing out upon every epoch or upon every iteration. So this is where the training actually goes on. We do a model.fit, and we pass in the X train, the Y train. So please take notes. We are passing in X train and then Y train to train the model. So this X test and Y test hasn't been introduced to the model yet. So X train and Y train, we pass in an epoch, which is the number of iterations that we want. Now, this morning, I had to run the model again. So eventually, I'm going to show you how to save your model so that because this one was very quick, but in terms of the computational time, okay, less than a few minutes, about 100 epoch is run, and we are good to go. But then some models will take about a day, okay, hours. So if you get a very good model with a very good accuracy and you don't save the model and you have to run it again, you are definitely going to waste a lot of time. So there are ways we can save it, and I'm going to show you today, because eventually based on our flowchart diagram, after doing that evaluation and checking that, okay, everything looks good, everything is okay, our model is very good, we then have to save the model so that we can have some kind of a program, okay? And then we can deploy to any other place that we want to have our system work. So everything looks good over here. Now, it turns out that when I ran it a couple of times today, I had a 90%, okay? Or a 90, I mean, okay, yeah, a 90%. So with this one, at least it was better than the accuracy I had last week, sorry, on Tuesday, which was about 80-something%. And then over here, we get the final width. So the final width looks a little bit different from the initial width. So I did bring back the initial width over here. So initially, the random width that was assigned over here was a 0.83. It ended up being a 0.66 upon the updates and the iterations that it went through. So things had changed drastically. Now, this is where we would want to do some prediction. So now look over here. I'm saying that model.predict, there's a predict method over there, and I'm passing in X-test. So initially, I've used the X train and the Y train to train the model. Now I want to do some prediction, and I'm passing in this chunk, X-test. So after passing in X-test, now this X-test, based on the data that we have, okay, we split the data sets. I think the testing part of the data was about 30%, if I recall. We can check or confirm that over here. Yes, the testing side was about 30%, which constituted about 45 rows. Yeah, 45 rows, exactly. So what we have ended up doing is, okay, we have trained the model with 105 instances of our data sets, which just look at this diagram and look at this as 105 instances, and this is just the 45 left. So we've trained the model, and in our training, we provided the input and its corresponding labels. That's what we did over here. The input and its corresponding labels. And then over here, we are doing a prediction. So now this prediction is definitely going to yield us some values. And in that values, which we saw was, okay, this one, for instance, we're picking up the value on the fourth count. So remember the counting starts from 0. So this is actually the fourth count. And in the fourth count, what is happening over here is giving us some values as we see over here. Now, I showed you on Tuesday that when we sum everything up over here, it is going to give us 100. So this is basically a probability distribution. And this one will also be very important in some models that will be doing some prediction, because over here, it is very clear that, okay, it's about 84% that this of class 0. And we know that class 0, based on the categorical change that we did, I think class 0 is Iris setosa. Good. And this is the probability distribution that it is Iris virginica, and this is the probability distribution that it is Iris vesicular, or yeah, the last one. Okay. Now we don't have too much of a problem over here, but then like in some cases where, for instance, maybe we are building this for some medical application or something of that sort, you would want to be very careful. Okay, probably you would want to give this in terms of percentages to the medical experts to also now use his human judgment to analyze the issues very well. You just don't want to say that, okay, the person has diabetes, so amputate the leg. No, you want to give out that, okay, there is about 50% chance that the person has diabetes, about 49% chance that the person does not have diabetes, and about a 0. something chance that it could be some other disease. So if I'm a medical expert, okay, or any other medical expert to look at 50% and 49%, this one is very close. So I should look into it very well. So probably that medical doctor would have to run some further tests to actually check. All right. So we did the prediction. So what we did over here was, okay, if we actually want to see the class in its entirety, all that we need to do is to do the argmax, which is just going to return the class for us. So over here, I defined an empty list, and I'm saying that, okay, I want to run an iteration through all the predictions that I have over here from ypredict, okay, all the 45 of them. And I would want to be doing an appending into the Y prediction list, but then I would want to have those labels. So I'm using the argmax to get the labels. So when we did the final one with the Y prediction, this is what we get. And if you have to compare this is our prediction, okay? Remember, this is our Y test. Our Y test is still seated there. We haven't used it yet. So now it is out of this prediction, because at the end of the day, all that we've done is, okay, given this value, and this value, I pass it through my model. What do I get? Now, whatever thing I get, I'm going to compare it with the original one, which is 0 over here. So if it is 0 as predicted and the actual is 0, then indeed my model is doing very good. But then if it is, for instance, 0, if it is, for instance, a predicted 1, but then the actual is 0, then that means there's some misclassification going on over there. Okay, so now everything looks good over here. We have the Y prediction values, and also we have the Y test values. But yeah, so that was where we ended the last time. So now let's save the model, okay? We can save the model, and then we can do some analysis later on. And yeah, so now let's save the model. So what I'm going to do is, in order to save the model, we can also import from, I think, Keras. So I can say from Keras.models, I'm going to say import save _ model, and then, so let me just import this one first. Okay, so I run this and everything looks good. So if I want to save the model, I just have to bring this method I've called out over here. Then I need to pass the name of the model. So the name of the model that we built is model. Okay, so that's what we did. And we are doing model.weight and stuff like that, because that's the architecture we specified over here. So the model was equal to sequential, and everything we did was model.add. So that's the name of the model. So the name of the model comes in here. So the model I want to save is model. And the question is now, how do I want to save it properly? Now, what I want to say is I want to have it like, let's say, network, or maybe ANN, okay, .h5. So this is probably a new file extension you are getting used to. So this is the H5 file extension, and I'm going to explain to you briefly what this H5 is all about. So now I'll do a shift enter to save the model, and I get some warning over here. It doesn't really matter, okay? So now this H5 or ANN.h5 has been saved, and that's going to be saved in my folder. So when I go back into the folder, I have this ANN.h5. When I open it up, it doesn't really open up because there's no application to do so. But we shouldn't worry about this, because I'm going to show you something very quickly. So let's assume we have this model. Yes, Enoch, your hand is up.
All right, I have a concern with the IDs we dropped. Okay.
Okay.
Along the line where the sequence was changed all over, so that the model doesn't learn in a particular pattern.
Yeah, sure.
Later on, when you want to trace some data points, in this case where you've dropped the IDs, how do you trace that? How do you trace and then compare your output predictions with the specific data points? I don't know if you get me.
Okay, all right, sure. So I get you perfectly. Now, what is happening is the IDs are not adding any value to our work, okay? And what happens is when we do the train test splits, okay, and it randomizes things, it also randomizes things alongside with their corresponding outputs. So look over here. Let me just show you. If we come in here and we look at the train test splits, okay, when we call the train test split, we specify that the inputs, the X input, and also the Y output. So it wasn't as if we're just splitting and randomizing only the X side, but it also was accompanied with the Y side. Now, why we also needed to drop the ID part is the fact that if we didn't drop the ID part, then what it means is we are going to have 5 inputs. And anytime we are now feeding some data for prediction, we need to specify 5 inputs. So the question is, okay, we are going to bring in an ID. And that ID, is it going to be 1, going to be 100, going to be 1,000? It doesn't really add anything up onto our system. So like Dr. Mill said, this is a computer system we are still dealing with. If you input garbage in, it is definitely going to do that computation to give you garbage out. So the ID is not adding any relevance. The relevance of our model prediction, or are we trying to train a model, is the fact that, okay, given the sepal length, the sepal width, the petal length, and the petal width of a particular flower, what class or what category does it belong to? Okay, it's almost like you going to the hospital. Every patient will definitely have some unique ID, maybe a folder number or something. And that's just for record purposes. But then if I want to train a model to do a diagnosis of a particular disease, the folder number has got nothing to do with the kind of disease that somebody may get. Okay, now let me also conclude by saying that if we actually want to verify that, okay, this was exactly like to make sure that even though things were randomized, but then the randomization, for instance, on the X train is actually corresponding with the randomization on the Y train. And let me just show you quickly. So now, before we even go to this, okay, we still have our X train. No, let's first do our data set. So our data set is here, okay? So now let's look at, for instance, this particular one. We had an ID of 1, and let me just copy these ones over here. So this was the first ID. So let me just do a Control-C. So if you bear with me, at least we know that this is the ID 1. This is sepal. Let me see. Okay, let me copy these ones too, and let me just put them over there. Okay, so based on what we know, this is the ID, this is the sepal. Okay. So this is how this data set actually looks like from the original data set we imported without dropping the ID and all those things. Okay, so now let's look at the X train. So let me say X train. So this is X train. I don't know if we can grab one over here, but then let me see, because this is randomized, so I don't really know. So let me do dot lock and see if I have one over there. Okay, so indeed I have one. So this, sorry, this is supposed to be 0 because this is the first one, okay, based on the indexing. Okay, so let me put in 0 over here. Okay, so 0 was actually part of the X train. Okay, now we look at the values we have. Okay, 5.1 is exactly 5.1 we have over here for the sepal length. Sepal width was a 3.5, is exactly a 3.5. Petal length was a 1.4, exactly 1.4. And then the petal width was a 0.2, exactly a 0.2. Now we don't have the species because this was X train. We have actually dropped that. So now let's check the species and see if it is the iris setosa is going to be 0. So let's now look at the Y underscore train, because that's where we have the Y train. Now the Y train, you see that this one too is also, okay, so this is the original Y train that has been randomized. Okay, this is the original Y train. No, let me check. X train, Y train, okay. So let me do a 0 over here. And we get a 1 over here. Iris setosa is supposed to be 0. Am I missing anything over here? Let me check. Iris setosa. Okay, let me see. Y train. This one is a 1, 2, 1, 1. This is 0. Let me see. Did I? Let me check this and see. So these are data sets. These are Iris Setosa. And then let me check if, how did I even call it? This one. This is the X inputs. Let me do the Y output. I think that's what I just did. So this is a Y output. And now they are very good. I think I was, let me cut this. So this is the where we did the train test plates. The things have become too many. Kindly bear with me. Very good. So the train test plates. So we did the X train and the X inputs and the Y outputs. So now let's do X inputs, Y outputs over here. So X underscore inputs. Okay, so this is the first one. So the first one, before we doing anything randomized, okay, we got to see that, okay, we had a 5.0, a 3.5, a 1.4, a 0.2, and then a corresponding 0 over here. This is the Y output, which has been changed into that categorical data, and then its corresponding entry over here. The index we see over here is 0. Now we do the X train, and we pass in an index of 0, and then we get those same values over here, 5.1, 3.5, and stuff over here. And let's do a Y train. I don't know why this is showing up this way, but then it's maybe I'm missing a lot of things are going around here. Let me see. Y train, X train. Okay, let me check this. One zero. Okay, that's exactly what I was looking. Okay. All right. So Enoch, I'll get back to you on this because I really wanted to select one specific one and actually demonstrate to you that even though the thing is done randomized behind the scene, it actually keeps track of whatever thing you brought up alongside. Please, are we okay on that for now? Is Enoch still here? Okay, I think his line has dropped or something. Okay, so now let's make progress from where we are. So over here, we have saved the model as ANN.H5. And like I did say, we have this over here. Now, one of the earlier things we dealt with when we started was to look at the Google Teachable Machine, okay? And over here, we were trying to experiment with building some models and seeing some few things. So now I'm going to go back briefly to this, and then we are going to see, I think we looked at the image projects, and then what else? Okay. Now, what I did was, or what we did at the time was, okay, we want to do some classification. So let's say I'm going to have a classification based on my pen and let's say my mobile phone. So mobile phone. And I'm going to show you this because of something interesting. So let me say, I'm going to show my camera briefly. So I have, let me try and get out of the frame so that I can have different images of the phone. So I have, this is the pen, okay, about 70 images. Okay, now let me go to the mobile phone. So there's my phone. And let me hold my phone and get different images over here as well. So I have different, okay, about 79. So everything looks good over here. And then I would want to see. So we talked about the epoch and the learning rate and other things. So over here, there's like a pre-built model. Okay, so things are going to happen behind the scene, but then it is giving you just an interface for you to plug and play. But over here, we are writing our code ourselves. So we click on this stream, and in about a few seconds or so, it should be done with the training. Okay, so it says preparing data. It should be done very soon. It says unresponsive, or why? Okay, so I just want to show you something of interest over here. Okay, so everything is done now. We can, of course, we're trying to do some of these things where we're doing the prediction. So over here, you see that it is 100% showing us that there's a mobile phone. If I'm to bring the pen, we get to see that it is now, let me put this very close over here. It is now showing us that this is the pen. Okay, now what we probably left out was to do, for instance, the export, okay, of the model. So now when I do the export of the model, we get to see that, okay, there are a number of ways we can do the export, okay? So we can export it in TensorFlow.js, which is some JavaScript, okay? Or TensorFlow, or the TensorFlow.lite, which is for embedded systems and those small devices. Now, what we see over here is, over here, after everything was done, okay, it is asking us that, okay, if I want to import and work with this, I now have to do model is equal to load. Then it says Keras model.h5. So we see this h5 extension being used over here because that's what ordinarily or by default Keras will give us. Okay, we can solve our model in h5 file format. Now this h5 file extension, this h5 file extension is it is an h5 is one of the hierarchical data formats, okay, used to store large amounts of data. So I mean, it depends on the kind of data that you want to store. And the data that we are storing over here in this particular instance is the weight, okay, that large matrix that we have over there. That is that structure that we want to save. So we need to save it in that h5 file format, and you can do some reading around it over here. But then the most important thing is we now have, so yeah, let me download this actually. Let me download this model. Okay, let me download this model. And you see it's converting model, whatever thing it is. And it should be done in the next couple of, okay, good. So now the model is downloaded. When I open this up in this zip file, we get to see a number of things. So clearly you could see that it gives me this, okay? It says the Keras model.h5. That is the h5. And I have some labels.txt. So the labels is basically going to tell me that, okay, I presented a phone as a label, and also, how do you call it? A pen also as a label. So if I'm to open this up and now open these labels up, you clearly see that the first label, which was based on the Python index counting, we see a 0 over here, and then the 1 was the mobile phone. Okay, so most of the things we are learning is nothing different from what people in the industry have built and are even deploying out there. But then this is the H5 model. Now let me just do a Control-C and bring this into our thing that we have over here. So this is the one we just downloaded. Okay, so you can experiment this on your own, and I expect you to do same. So now let's come back here and let me just close this one and do some analysis of this. Okay, so let's assume we come in here, maybe on another day, open up a new notebook, okay, and we have the model saved. It can be saved, put it on a Google Drive or any other place. And now I just want to load the model and now start using it to make predictions. All that I can do is, okay, I can say, I want to import Keras because I need Keras to make this work. And then I'm going to say, so let me first of all import Keras over here. Okay, so I'm going to say from Keras.models. Remember when we wanted to save, we imported the save model. Now we want to load it. So I'm going to import load model over here. So I'll run this, and now I can now bring this load model, Control-C, Control-V. Which model do I want to load? Okay, the first I want to load is my original model, which is the ANN.H5. So I come in here and say, okay, I want to load ANN.H5. And now I want to save this in a variable called, let's say, let me call this flower model because this is the iris model. Okay, let me call this iris model. So I run this, and now I have my model back. So now I can do iris model or iris underscore model dot summary. Remember the summary. Now when I run this, I get the same summary as I did before when I first, how do you call it? Built it. Okay, so you see that when I did model.summary, when I initially built it, I had, okay, this is a sequential model, blah, 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 the dense layer, the whatever things, the parameters over here. And that's the same thing I'm getting over here because those weights were saved. And now what I want to do is also to do, for instance, iris.model.get underscore weights. And now when I run it, it is the same weight that is going to be saved. So this was actually the final weight. So we see that, okay, with the final weight, we have a 0.66. And over here, when we built it the first time, and we're checking after running this, updating the weight through the learning process, we see that the final weight, get weight, final one is what we see over here. So the point is, at the end of the day, it is the weight that's going to be saved. Because back to the scenario I gave on Tuesday with regards to that social science project, when people are analyzing things, or even when we are using our brain, because sorry, this is an artificial neural network model, which is inspired by how we analyze things with our brain. Okay, we always want to put some people will call it a cost, okay, a cost or a weight on our decisions. So for instance, you wake up and maybe you want to wear some dress. You ask yourself, hey, the weather is hot too. If the weather is hot and whatever thing you are going to wear, you put some cost on it or you put some weight. Okay, if the weather is hot, then I should wear something light. If the weather is cold, I should wear something heavy. That kind of analysis. So it is the weight that we are saving. And whatever weight that we have, any new data that we bring on board is now going to be analyzed or passed through these weights, and we are going to get some prediction. Now, let me also show you something interesting, because what we've also ended up doing is, okay, we went on the teachable machine and we now have this Keras underscore model.h5. So we can also load this one and see how things are structured in there. So over here, I'm going to call, use the load model over here, okay? And what I want to load is the Keras underscore model.h5. That's the one we built. So I'm going to call this something like Keras underscore model is going to be equal to this. So I'll run this, and okay, it says everything is okay, but then it is giving me a one. It says training configuration found in blah, 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 blah. Okay, not compiled. Compile it manually. Okay, no problem. So now let's do a Keras model, which is from this, the one we just brought in from the teachable machine dots. Let's do a summary and see how this behind the scene was also structured. So behind the scene, look at the number of parameters it had at the output layer. The moment you see this number, because look at this. This one, we are the one who built it, so we know that, okay, we just used 4 neurons over there. So those were the connections, okay? Over here, we see quite a huge number, 1,280. And once again, you realize that, okay, with the output layer, because we were just using 2 labels, the pen and the phone, it also specified that, okay, as for that one, it's just supposed to be 2. And that's the same thing we see over here. But then with this one, we specify the number of output neurons that we have. So over here, once again, like, of course, we are engineers, so sometimes we need to go into the minds of how things are engineered. So the point is, okay, the system was built in such a way that, okay, the number of classes you select, then automatically is going to specify that number of, the output layer for us. And then perhaps maybe these values or the other architecture is randomly selected by some parameter, okay, that they use behind the scene. Now we can also do a Keras dot the Keras model dot get underscore weights over here. And of course, this is going to give us a very huge, because remember this one was, or we had 1,280 synaptic weights, okay, or connections. And for which reason we have a whole lot over here. We have a whole lot over here. All these random weights that were selected and adjustment was done to the weight and all the other big numbers you see over here. And that's what we have. Now, later on, when we deal with images very well and we do our classification models, we're actually going to build one. We are going to write the code from scratch, do some few analysis of it, and also use one that we are going to use, the teachable machine, and do that comparison and see how close accuracy and our predictions are to the ones that are professionally optimized. Okay, so now let's get back to what we have over here. So you get to see that a lot of the things we've kept on saying are not just like quick analysis stories. They are things that happens behind the scene. Now, you are the engineers, so you should know exactly what is happening, and if there's a problem, you know how to fix it one way or the other. So maybe somebody gives you a model, and the person, oh, I'm doing image classification, and I want to classify images into A and B, only A and B. And then the person gives you do a model.summary, and you see that, oh, there's about 5 output shape neuron over here. You clearly have a better understanding that, okay, if you just want to classify into A and B only, then you have to do some changes over here. So you go back into the code and you apply the necessary changes. So now we get back over here. So now we have, let me just delete these ones. And now let's look at some few analysis that we can do. Because after our model is built, we'd want to perform some analysis of the model, okay? Now over here, we only have the training accuracy. We only have the training accuracy. And with the training accuracy, it is not enough, okay? Because as for the training, it is always not going to be enough. It is only when you test yourself, that is where you begin to know that, okay, the training that you did, you've actually trained well. So a lot of the time, we'd also want to test our accuracy, okay? So we can do an evaluation of it. So now we can do model.evaluate. Evaluate over here this way. And what do we want to evaluate? Let me just get rid of these ones. We want to evaluate with our X test, because that's what we can use to evaluate this model. So now when I run this, we get some numbers showing up over here, okay? So we get, for instance, a loss as this and an accuracy showing up over here to the power something, which is not really making sense. But then let me just see what Okay, so now let me say accuracy. So loss for my accuracy is going to be equal to this. Okay, so now let me just, sorry, loss. So our loss is, practically 0. And the testing accuracy, I think I'm missing something over here. It's also 0. Okay, so let me look at this. Okay, so we are putting in the X test, and also let's put the prediction, because it is a prediction that we want to check out over here. So X test, and then what name did we give the prediction? Okay, so the Y prediction. Let me check this one and see. All right, good. So this is exactly what we want. So we want to check the testing, okay? This test part of the data with the predictions that were made. And we get to see that with the loss was very minimal, okay, a 0.39, but then the test accuracy was about 100%, which wasn't bad, because already we are getting a 90% over here. Okay, if you have to run this on your system, your values will be a little bit different. But then there's more to this, and let me just quickly run through some of the preliminary analysis that you can do. Okay, so we can see from sklearn dot metrics, we want to import, we can import confusion metrics. So we are going to import confusion metrics this way, and we are going to import one we call classification report. So this classification report is going to give us a lot about our classification model that we built. So I'm going to bring this classification report out, and then what do I want to put? Okay, I want to put out my Y test and the predictions and do that comparison carefully. So I want to put my, sorry, I thought I had this copied already. So yes, I want to put up my Y predictions and my Y test, because those are the ones I want to compare. Now I'll run this and I get something interesting over here, but then let me just save this in a variable called report is going to be equal to this. And now let me do a printing of reports. Okay, so now this looks a little bit better than what you saw. Okay, so over here we are getting a little bit more, and per our schedule we are definitely going to go deep into what we have over here as a model testing and performance, the model evaluation and visualization and all those things. Okay, but this is just to give you a sneak peek into this, and I'm doing this because at least we've built a model. We need to do some preliminary analysis of it and see how it is doing. So yes, we have for instance the precision, the recall, the F1 score, and the supports, and the accuracy we see over here, and the macro average and the weighted average and all those things over here. Now this may come in handy depending on the kind of analysis you'll be dealing with. But so far, everything we've been dealing with is accuracy, okay? And sometimes accuracy may not paint the true picture. It may not be a true reflection on the ground. Now, the reason why I say this is we all love Ghana Black Stars, okay? Back in the days when Asamoah Gyan was who he was. Imagine you watch, probably you didn't watch. And let me use this example. I think Asamoah Gyan's time is gone. Let me use this example. The Chelsea fans will agree with me more. Those of you who support Chelsea, you know that your main striker is Nicholas Jackson. And he misses a lot of chances. He scores a lot of goals. So imagine you don't watch a Chelsea match and you just hear the score line after the match. And then somebody tells you, oh, Charlie, the match, Nicholas scored 2 goals. You'll be like, hey, Charlie, then he was the man of the match. Chelsea won by 2-0. He scored 2 goals. And somebody can tell you that, Kai, he didn't do anything, and you'll be surprised. Now, you only get the confirmation if you actually watch the full match. And maybe upon watching the full match, you realize that, Nicolas had about 10 penalties and only scored 2. Automatically, it changes your whole perception about his performance on the day. Because the 2 that you had initially, based on the scoreline, was like, oh, he did well. But then when you realize that, out of 10, you only scored 2, you converted 2, and you missed 8. Then if I'm the coach, next time if we have a penalty, I'll think twice before I put you behind the ball. That's the whole concept of really trying to holistically analyze our model or our model's performance. In a sense that accuracy is only giving us one side of the picture. We also want to check how inaccurate we were in some instances. So this is where we come. So for instance, precision is giving us, okay, how accurate we were. Now recall, in a nutshell, is also going to give us the other side of the picture, how sometimes inaccurate we were in our predictions. Then the F1 score is what we refer to as the harmonic mean. So when we put everything together, how good you were, okay, combined with how bad you were, we find the average. Then we get to see a true reflection of your performance. So in the case where Jackson had 10 penalties, that means, and he scored only 2, that means he was good on 2 occasions, but then he was bad on 8 occasions. If I'm to find the average, the harmonic mean of his good and bad, I'll definitely end up concluding that, oh, well, even though you scored 2, but then your performance was poor. And that's exactly what you want to do, because at the end of the day, regardless of how good or how bad our model is, it is always not going to be 100%. So there's going to be a lot of correct, there's going to be a lot of wrong. And this classification report will give us that analysis. Now, like I said, this is just a sneak peek. As and when it becomes necessary and we build a lot of models, we're actually going to see different methods we are going to use to analyze our models. So this is just to make you understand some few things. Now, remember, I also brought in the confusion matrix, because this confusion matrix is also going to help us. So now let's plot a confusion matrix of this. And once again, it is going to be what the actual was and what we predicted. So over here, let me call this matrix is going to be equal to this. So I'll run this and I'm going to get some values over here. So in here, I'm getting some cool values and I'm going to show you why. So over here, let's do a plot, okay? So remember, I already have Seaborn over here, and I just want to plot this on a heat map. So that heat map is going to give us that. Remember what we did with the correlation thing over there. So now I run this and we get this. Now let me put in the values over here. So I'll say anot, which is the annotation, is going to be equal to true. And let me do plt.show over here. Okay. So over here, the values that we see over here based on this confusion matrix is what we see. So over here, the first quadrant we see over here is having the 16. This one is having the 10, and this one is having the 12. We are seeing some 7 over here. Don't worry, I'm going to explain why we are getting zeros over here and we are getting some values filled up in here. Now, let me just also do a plt.title. And we already know what this is. So this is going to be the confusion matrix for our title. And let me do plt dot ylabel, and this is going to be the true label, okay, or the actual label as you have in some books. And then let me do .xlabel over here, and this is the predicted. So I'll run this and it says the label, okay, the spelling of label was not accurate. Okay, so now this is what we have. And this is also giving us a little bit more in terms of our analysis so that we get to understand the true nature of why certain things went a certain way. Okay. Now, what I'm also going to do is, I'm going to come back to this, is I'm going to have a pair plot. Remember, I spoke about this pair plot and I said there are some inherent things that we can look at over here. So with the pair plot, what I need is I need, okay, the data set, which is the original data set, and I'm going to specify a hue of the species. I think we saw this the last time. Then I'll do plt.show. So whilst we wait for this pair plot to show up over here, let's look at the confusion matrix. Now, over here on our y-axis, we have the true labels and we have the predicted labels on our x-axis. Now, what we see is that, okay, the first class is 0 over here, the second class is 1, and the third class is 2 over here. Based on the Python indexing, we already know this. Over here too, that's the same. Now, we see that we have 16 over here. This 16 is also coming from this support. So you see that from the first label, we had a support of 16. What it means was, okay, from the first label, at the end of the day, everything summed up to 45. And out of that 45, how many of those 45 instances were used in our testing with regards to the first label? And how many were used in our testing with regards to the second label? And also, how many of them were used in regards to the third label? Now, remember, based on the train test splits, everything was randomized, and for which reason we cannot know it offhand, except for the fact that we now have our opportunity to use this classification report to see. So over here, you can see that, okay, out of the 45 that was randomly selected, at least we had 16 of them that were Iris setosa. We had 17 of them that was Iris vesicola, and we had 12 of them that was Iris virginica. Okay, so now what is happening over here is, okay, so out of the 16 for the first one, which was Iris setosa, this was the actual 0, and all the predicted was also 0. So the intersection was that, okay, everything was accurately predicted over here. Now, in the case of the second class, we had 17. Bear in mind, we had 17 of them. Now, the question is, okay, this is the actual or the true label. Out of the 17, 10 of them were predicted over here as 1. And unfortunately, 7 of them were misclassified. So these were the true labels. They were supposed to be 0 over here, but then they were predicted as 2. Sorry, they were supposed to be 1 over here, but then they were predicted as 2. And then in the case of the third class, we had 12 of them from the support, and all of them were indeed predicted as 12 over here. So now the problem actually has to do with the second class and the third class, which is 1 and 2. And that's what we see over here. Remember, I told you this, that in our analysis, the first class, which is Iris setosa, if we look at all the blue spots over here, they are widely separable from the others. But in the case of Iris vesicola and Iris virginica, a lot of them are intertwined. So over here, look at this particular one. You will see that a lot of the yellows, the oranges and the greens are intertwined. But then this one, there's a very clear distinction between what will constitute an Iris setosa. But then in the case of Iris vesicola and Iris virginica, we are going to have a lot of issues over here. So now the point is, even just looking at this diagram in terms of the plots, the question is, given maybe a prediction that is falling in this area, if the prediction is falling in this area, we can confidently say that this is going to be an Iris setosa. But then if it is falling in this area, then chances are it can be an Iris vesicola or an Iris virginica. And that's the reason why we are having a lot of misclassification over here, in a sense that it was supposed to be 17 all over here. So now the general rule of thumb is, okay, when you plot a confusion matrix, and indeed you have a very good case of a confusion matrix, the major diagonals should contain the maximum values, okay? So over here, these are the major diagonals. We have 16 over here containing all the values that were used for testing, and it correctly predicted everything for Iris setosa, because those ones are very highly separable if you look at all the pair plots we have over here. I mean, we can draw a line over here and there's no mismatch over here to, okay, we can get one over here and there's a little bit of an issue over here, but then it is not as obvious as the ones we see over here, which are intertwined, okay? In this case, we see that this one is separable. These ones are a little bit joined up over here. These ones are separable. These ones are a little bit mixed up over here. And same applies to the ones we see over here. Okay, so the visualization is helping us reinforce our knowledge and understanding of why we may have some misclassification. So, for instance, if you are presenting this in terms of some medical diagnosis system that you are building, you need to be able to explain that, okay, if it is, for instance, an iris setosa classification, then we are 100% sure, maybe we are 90% sure that that one there, we don't have any problem with it. But in the case of the virginica and the vesicular, there could be a misclassification, and that is where probably we need to look out for. So if you go back to what we see over here, you realize that with the iris setosa, everything was 100%, 100%, 100% over here. The precision was 100, the recall was 100, everything F1 score 100. Okay, but in the case of the first one, which is the second class, the precision in terms of how it was able to correctly predict, it was 100% over here. But in terms of how it was unable to correctly predict or how wrong it was a 59% over here. Because clearly we saw that, okay, it was correctly predicting 10 over here and wrongly predicted a 7, which was quite significant. So the F1 score is now giving us the harmonic mean. So when we put everything together, how good you were and how bad you are, we are getting about a 74%. Then in the case of the third class, we saw that, okay, in terms of its accuracy or precision, we are getting a 63% over here. But then in terms of its recall, it wasn't making a lot of mistakes. That's basically what this one communicates. And for which reason, we can see that, okay, the overall, the harmonic mean, which is the F1 score, is about a 77%. Because we presented 12 over here. Now, what we saw in terms of the accuracy, because remember our accuracy from our training is about, a 90.48%, okay? And that's precisely what we see from our classification report if we are to analyze this from the weighted average in terms of its precision, the accuracy. Now, if you have to look at it from the other side, how inaccurate, because the more inaccurate you are, then you are dropping a little bit. So over here, we get an 84%. And then with the harmonic mean, we are getting an 84%. And also with the macro average, we are just looking at it from another angle. Those are the things we see over here. So our time is up, and there were some few things I wanted to touch on, but at least what we've done up to this point, because we've all agreed that we are going on a break for maybe a week or two. What we've done so far, at least, we've covered everything we see in this block diagram. We've done some pre-processing, data analysis, and all those things over here. We've seen the splitting of the data set. We've built the architecture of our model. We've done the training of that model. We've done some evaluation. We've saved the model like I just showed you. And then we haven't deployed the model yet, but then we've done some analysis of it. Now, what we can do is, now that we have the model, we can still be doing model.predict. And the model.predict is going to take in 3 inputs. Iris setosa, 4 inputs, the sepal length, sepal width, petal length, petal width, and all those things, okay? So let me say I can have something like new data is going to be equal to np.array. And remember, it is going to be multiplied with some numbers in there from the weight. So we don't have to just put in a list, okay? And this is just going to be, I believe a 1D array will be okay over here. So now I can do, let's say, a 2.3 for the sepal length, a 4.5 for the sepal width, 0.6 for the whatever, and a 3.4 for whatever. Now, if I want a prediction, I can put this over here. And now let me run this and see. I have an issue over here. It says, okay. Now, these ones are going to be very common if we don't present our data in its right shape, okay? And let me just get off this and see. It says, okay, so the once again, it is the dimensionality issue that is prompting us. So I think, let me just do this way. Okay, let me just pass it out this way. Yeah, I think it needs to be so. Sure. So I'm just putting it in some double list stuff over here. Now, this is what we get. We are seeing that, okay, in terms of the probability distribution, this one is very small, the first class. But then in the second class, it is telling us about a 45% sure that this is going to belong to the iris vesicular. And it is about 54% that is going to belong to the iris virginica. Now let's look at this objectively, and let me just come back here because that's the last thing I'm going to do so that we have a proper analysis of everything that we are dealing with. Okay, so let me just copy this one. So these were the inputs we provided. So I'll do a Control-C and a Control-V. So the first parameter we have over here is the sepal length, and we are saying a 2.4. And the petal width was a 4.5. So now let's keep these two values in mind. The sepal length, 2.4, sepal width, 4.5. Now, sepal length is what we see over here. And then the sepal width is what we see over here. So now let me just shrink this a little bit. It's not shrinking. Okay, so now this is the sepal width and the sepal length. So the intersection is sepal width. Okay, so this is the intersection. So this is the intersection, okay? And the values we have picked, this intersection is a 2.4, is a 2.4 and a 4.5. So with a 2.4, that's the sepal length. Okay, the sepal length was a 2.4. Now look at the plot we see over here. Let me check this one again. Sepal length, 2.4. Sepal width, 4.5. Okay, so sepal width. Okay, so now let's check this. Sepal width, the 4.5 is somewhere around here. Please take your time and actually analyze this, okay? So let's say the sepal width is somewhere around here. If the sepal width is somewhere around here, okay, and okay, let me just pick up petal width, okay, petal width and sepal length, because those are the ones we can simply pinpoint over here. So the petal width is the last value, 3.4, okay, and the sepal length is the first one. So 2.4 versus 3.4. Okay, 2.4 versus 3.4. So now when we do a 2.4 over here, the 2.4 is for the sepal length. So sepal length 2.4. 2.4 will fall somewhere here. Okay. 2.4 will fall somewhere here. And then the 3.4 with the petal length. Now look at 3.4 petal width actually. It's taking us 3.4. It's taking us above. So if we are to actually plot this, it's actually going to take us above here. And it is going to be very close to a green. Okay, above here is going to be very close to a green. So when we look at this, the green is the iris vesicular, which is, in terms of the class, this is 0, 1, 2. And that's informing a 0, 1, 2. So we are getting a higher probability over here that it is about 54% that this is an iris, which one? Virginica. All right. Now, if you are to compare, let's say, the petal width and let's say the petal length, the petal width is this one and the petal length. So a 0.6 and a 3.4. So the petal length, this is the petal length, a 0.6. A 0.6 is somewhere here, petal length 0.6, okay, somewhere here. And a 3.4. Once again, the 3.4 is going to take us a little bit up because this is ending at a 2.5. So a 3.4. So it is more closer to the greens in terms of the class, which is the third class, or in terms of the Python indexing, is going to be of class 2. And so forth and so forth. So you can actually test with some different arbitrary values of your own. And you're actually going to see that if you actually to look at its corresponding petal length and petal width values, and actually do an eyeballing or maybe a plotting of it, you're actually going to see that, okay, the class it predicted is actually going to be within that range. And we are going to see that, okay, everything is beginning to make sense over here. But the reason why we are getting a little bit of the misclassification in the second class technically is because of the fact that a lot of the values over here are closely intertwined. So for instance, if we were just to pick up, let's say, a value like this, even though this is a green, somebody can make an argument that, okay, it can also be an orange. Okay, this one, for instance, because majority of the oranges are here. So these were probably outliers. And if the model doesn't know, it is just going to misclassify them one way or the other. Okay, I think we can end here, but then it is good. Some of these recordings are here. Okay, Enoch, I'm going to come back to you. It is good some of these recordings are here. And please go back and go and review them whilst we are waiting for our next move, depending on where school is going to reopen and other things. Okay, Enoch, please, your question.
All right. So I know about the ROC curve, which is usually for binary classifications, where you find the area of the curve to
Sure.
assess the model. In this case, where we are classifying three different classes, is that also applicable in a way?
Okay, so yes, it is applicable in a way. And those the ROC curve is basically going to plot a curve of our true positives versus our false positives. Okay, so that's going to be that one. And like I rightly said, when we come to the performance metrics, we are definitely going to delve more into that. And every artificial neural network model will have its own unique every algorithm will have its own unique way of doing an evaluation. So whilst some matrices, so for instance, and let me give you a typical example. This is the reason why this is working for us in terms of plotting the confusion matrix and all the things we see over here is simply because we are doing classification. If this was regression is, let me come back here. For instance, this one, okay, where we're doing a regression, okay, we're predicting a particular value based on the learning rule that we have over here. This is not a matter of, okay, 20 of them were classified as A, so we are comparing our B to check if it is. No, we cannot use classification to check. So over here, and I hope you remember very well, we are actually going to look at the root mean squared error based on secondary school, okay, or the mean square error, in a sense that, okay, if I want to check how good this is, I would want to check, okay, how far are my points from, for instance, my line of best fit. So over here, you see that, okay, the distance between this point and this line is going to be a little bit huge, but then over here it is small. It is a little bit small over here, a little bit small over here, and these ones are very, very, very insignificant. So you realize that, okay, if your how do you call it? The distance between your line of best fit and your actual values are small, if they are minimal, then it means that, okay, your prediction is doing well. But then if, for instance, maybe we had 1 point over here, another point over here, definitely those are also going to constitute, and that's going to be a different metric that we use. So every model has its own, or every algorithm has its own unique metric that we use for analysis. It turns out that this one, the one we are currently looking at, which is a simple classification problem, this one is going to work for us because we have some classes and we can actually compare in terms of accuracy. That's okay, we're expecting a 1, we got a 1, okay, then we are correct. We're expecting a 1, we got a 0, okay, then this one is wrong. So at the end of the day, we can sum all the correct and sum all the wrong and actually look out for accuracy and stuff like that. But in other models, we are going to see other things. And it's good you brought the ROC curve. We are going to look at the ROC curve and other things in order to make sense of the models that we build. Please, I hope you are okay with that.
Yes, sir. Thank you.
All right, thank you very much. Please, any other question or contribution or suggestion? Okay, so in the absence of any contribution or suggestion, Dr. Mills, I think we can end here today. We've taken a lot more of their time, about 20 minutes. And then
Okay.
Yeah.
All right. So thank you very much. So if there are no questions or comment or contributions, if there are no further questions or comments or contributions, we will end here. You have a pack of things that if you want to go and reflect on them, you have a pack of things to reflect on. So that will be the end for the session. We'll be waiting and standing by for your, after 1 week or two, standing by for your further confirmation on when you want us to continue. On that note, we wish all of you a good rest and a holiday. Okay, thank you to everybody.
Thank you very much, sir.
Thank you, sir.
Okay.